I came to know Dr. Williams. I was on a tour at Oak Ridge National Lab where they have a huge presence there in additive manufacturing. On a tour of the lab, and I asked some of the folks there who's doing cutting edge research on this, and Dr. Williams' name came up, and so contacted him and asked him if he'd be willing to come speak, and he so much obliged us and brought his students with us from the mechanical engineering department. He is the director. He's assistant professor, and he's the director of the Design, Research, and Education for Additive Manufacturing Systems in the DREAMS Lab, and the co-director of Virginia Tech Center for Innovation-Based Manufacturing, CIBM. For his AM research contributions, which is additive manufacturing, he was recently awarded the 2012 International Outstanding Young Researcher in Freeform and Additive Manufacturing Award, presented by the International Solid Freeform Fabrication Symposium. In addition, he was named the recipient of the 2010 Emerald Engineering Outstanding Doctoral Research Award in the area of additive manufacturing, and was recently selected to co-chair a session on additive manufacturing for the 2013 National Academy of Engineers German-American Frontiers of Engineering Symposium. There's a lot of other things in his background and his resume. I won't read them all, but please welcome Dr. Chris Williams. We look forward to hearing your talk.
Well, thanks again, everyone, for being here. And really, what I want to do today is sort of pick up where he left off and talk about this transition from rapid prototyping to additive manufacturing. I'm really happy that we have some high school students here with us, because these are the folks who are really going to help transform this, and they're the ones who really understand the potential. So let's talk really quickly about this. And what this technology was originally created, it's sort of catching everyone's attention all of a sudden. But it's actually been around since, I think the first technology was commercialized in '88. So it's been around for over, over 20 years. And it was originally created for this idea of rapid prototyping. This idea that I can go from my idea. So this is one of my students, sophomore mechanical engineering design class. Why do I carry around these bulky keys? Why don't I just have a Swiss Army knife for my keys? So they have this great napkin sketch. They do this beautiful CAD model. They've made it modular. I can slap on different university colors. They win best in show. So as a reward, we say, well, we'll print your model for you. Their model comes out wonderful, except for the fact that it's about 4.5 inches long. Now, on the screen, that looks completely reasonable, but when it's in their hand and they try to put that in their pocket, it just doesn't quite work out. So it goes back to exactly what Terry was talking about. And a lot of companies do this. Reebok uses this, and they actually print their shoes before they go to production. Burton Snowboards prints their bindings and actually will put them on the snowboard to ride them down the mountain before they go to full production. Now there's a transition, though, that happened in the mid-90s where we said, well, we don't want to just do prototyping, we want to do manufacturing. So we did a transition to this thing called rapid tooling. Now in rapid tooling, what you're doing is you're actually printing parts that can be used as tools for traditional manufacturing processes. So actually at Virginia Tech, we have a new foundry that just opened last year. We can pour up to 300 pounds of steel there. It's a great facility. It's a beautiful facility. It's a wonderful facility because it shows you how clean foundry work can be. So here's our object printer. It's an inkjet printing process that prints droplets of a resin, a photopolymer resin, that are cured by UV light. And what we're printing there is a little set of coins with all of our gates and runners there. And that's something that we then pack sand around, traditional foundry sand. Then we can go through and do our traditional foundry work of our metal pouring and our mold breaking out. And so we're using the additive manufacturing as a means of supporting traditional manufacturing. Because traditionally I would have to have machined that pattern, packed that in sand, and I've got this pattern that sits on my shelf in my air conditioning in my inventory house. And I, in theory, could have made every single one of those coins have each of my students' names on them. It's easy to customize. So the end result is, nice aluminum products. One of the early customers, famous customers of Additive, was Jay Leno. Why would he, of all people, care about this technology? He's got this car collection, yeah. And what happens when one of his cars breaks down? Can he just go up to this, Sears catalog or go to call up Ford? Hey, I have, you only made 3 of these cars in the world. I need a replacement part. So what he does is he takes that part off his car. He 3D scans that, digitizes the model, can go into that point cloud, and then actually fix the part digitally, Then he can print that out of an ABS polymer, which was mentioned via the FDM process, coat that in a ceramic slurry, and then pour your aluminum in that. That ABS has a low melting point. We just melt that out. It's basically lost wax, but with polymer. So for tooling purposes, this technology can support that. But that's not quite enough, and we'll talk about that transition. So here's a 2009, it's a little out of date, about how the technology is being made, where it's being used. And you'll see that huge space in medical and dental. We'll talk a little bit why that's the case. The big three at the time were probably our first big adopters of the technology, and of course aerospace as well. But how is it being used? Well, again, a large majority is this, prototyping. How does it look? How does it feel? Do all the pieces fit together? And you'll start seeing patterns for metal casting, some other kind of tooling. People have done some low volume injection molding with this technology. But what we're really starting to see a big boom in is in direct part production. That's the goal, is to use these technologies to directly fabricate end-use products. And that's a pretty big request for a bunch of technologies that were originally meant to just make little models. So with this, and it's all, of course, it all comes through research and ASTM, right? We have a manufacturing technology without any standards. So the very first order of business, which was about 2 years ago, was the creation of even the agreed upon word, because we call it rapid prototyping, we call it 3D printing, we call it solid freeform fabrication, we call it layered manufacturing. The official terminology is additive manufacturing, and you can see all these synonyms that came with it. But it's to really harp on the fact that this is about manufacturing in goods. That's the ultimate goal. And also, you'll notice we lost the word rapid. We'll talk about that as well. But let me sort of continue on about what was mentioned earlier about this power. Why is it that this is something that we think is so important? There's a lot of power in this layer by layer approach. All right, so you all are here. So so this is fun to ask these folks. This is the product that we've printed. On the right-hand side is as a cross-section, an image of a cross-section of the product. And the great thing about this technology is there is no fixturing. I don't make any fixtures. I can make this part in this orientation, this orientation, this orientation, any which way I please. It's just a matter of slicing into layers and hitting print. So what I'm showing you is that product can be printed like this, or it can be printed like this. So the layer changes. So for those of you who are manufacturers, could you make this? This is called a chiral cellular design. Can you make that? Anybody? Does it have a draft angle? That's one question. I'll say no, it doesn't. And you say very easily. Not very easily. Why not, though? So we got a lot of material to remove. But I mean, the nice thing is it doesn't have any draft angle, but maybe I could go in a machine, each pocket, and maybe I would have to sort of fill at these corners, but maybe we could do it. It would take a lot of time. What about this pattern, this shape, where we have a swept honeycomb? Again, I can print it like this, I can print it like this. So I can't take my machine bit and spline that. I'd have to make the tool first to be able to injection mold, and even if I could do the injection mold, I'd have to pull the part out of the mold like this. To the printer, it's just a bunch of wavy lines or a sort of a grid that just sort of shifts back left to right. Okay. What about this? So, I'm going to sneak behind the column here. And this was mentioned by Doug earlier in his talk, this idea of what we call cellular materials. These are very lightweight, stiff, but yet strong materials. These are the kinds of materials that we see in nature, right? Bone, coral, wood. They're not solid slabs of concrete. They're all lightweight, but yet stiff and meet the needs. So to our printer, this structure is nothing but a series of ellipses. And what I'm doing is showing you an animation every 5 layers. It's just a bunch of dots. Your home inkjet printer can do that. It can print a bunch of dots. And all we're doing is stacking those pieces of paper on top of one another. So I'll pass around. This is a part printed on an object part. You can sort of see how fine we can go. And it goes back to this thing of it really reshapes the way in which we do design. So in the lab, we have a sort of field of dreams, tongue-in-cheek quote. Just, if you can draw it, we can print it. And actually, what I'm getting at is, I don't know how many of you are, I'll ask my students who I know can use CAD, how many of you can draw this? we're getting to the limits where manufacturing is not the barrier to entry. It's the design is the barrier to entry. If you can conceive of this shape, then we can make it. So this is the transformation of the field into this additive manufacturing, which is all about doing design through modeling and simulation, doing it digitally. So here's an example part relative to this community, perhaps. This is from our Formula SAE car. It's the students who design, build, and race a full functional open-wheeled race car every year. This is their intake manifold. And I had a student who wanted to redesign that intake manifold such that the geometry, the runners are tapered, the plenum is tapered, such that he has even airflow across all 4 cylinder heads. He does his computational fluid dynamics analysis. He shows that this geometry is better than the traditional geometry. Gives him the better even airflow across all cylinders. But how does he make that? How do you take aluminum and taper it? How do you weld aluminum with beautiful fillets? If you're a skilled machinist, you might be able to do that. If you're a bunch of undergraduates or even graduate students, or even if you're a community college graduate, this is not easy to do, right? So it's all done digitally. Then you just print. Now, what we did in this part is we actually printed a FDM ABS part. Now, again, I talked about a lower melting point. This would just completely melt right on the engine block. So what we do then is we just wrap it in carbon fiber. We actually wet bag it, or vacuum bag it with a high temp epoxy, soaks into that part, improves its heat deflection temperature so that you can directly use that. No machining. And we know that we get the geometry that the design says we can get. And before, we couldn't even conceive of the geometry because we had no means of making it. That's the power of the technology. That's what we refer to as additive manufacturing. Let me give you probably our best known example of an industry. Maybe our high school students especially are familiar with this. How many of you are familiar with the clear braces? Right? Invisalign? How in the world, if you're a manufacturer, how do you make personalized, not custom, personalized braces every 2 weeks for hundreds of thousands of customers across the globe? Are you going to are you going to machine a mold to then cast on a polymer? Or do you instead give them some clay, bite into that clay, and then 3D scan that, go to your dentist CAD, fix that digitally, and then print a mold, which you then cast your FDA polymer? People don't know this, but when they have these invisible braces, they're not wearing 3D printed parts. They're wearing parts that were formed around, almost like your vacuum forming process, right? So we don't yet have an FDA-approved polymer that you can put in your mouth. Our surface finish is not quite there where you have nice clean. And also, our polymers aren't perfectly clear yet. People don't want to buy braces that make their teeth yellow, I guess. But still, they're using a technology there. Another, maybe on the other end of the spectrum, from young teenagers to not so the rest of us, these new invisible hearing aids are all 3D printed goods. Your ear canal is unique to you. That is your fingerprint. So they stick a piece of clay into your ear, pull this out, 3D scan that, and actually print the shell of the hearing aid, stuff it full of electronics, and now you have a custom fit hearing aid. Again, how do you provide custom goods to the masses? This is the technology that allows that to happen. So Terry did a great job of talking about a lot of the polymer processes, and I was asked to talk sort of more about the other end of the spectrum. And you'll notice that my diagram looks very similar to the one he just showed, right? So he was talking about a nylon printing process. We have powder nylon, and we have a laser. That laser melts and then one single layer of the nylon, and then we have fresh powder that raises, and we have a roller that sort of pushes the fresh powder across. And we give enough energy in the next layer to fuse those two layers together. And at the end, we dig the part out like an archaeologist. But I'm showing the same diagram because you can do the exact same process, just a bit higher powered laser, and do titanium powder, do tool steel powder. And so that's the same process. And again, as was mentioned, when you're doing complex overhangs that are typically impossible, to us that's just loose powder. We just shake that part out. Terry's got a much nicer brain view that's bigger here, and so I'll pass this around. This is, again, if you sort of hold that from 2 points, you can rotate one wheel and they'll all rotate. It's printed by this process in one print. Well, what does it look like when you're doing metal? This is a new process called laser cusing. What you're seeing there is a laser sintering titanium. So this is the recoating blade putting fresh powder over. And again, don't blink. One layer is printed. And out of that build comes a fully dense metal part. And this is what's interesting about this really quickly, just to tie this back to lunch. This company has always been an injection molding company. They're in the business of making the molds for injection molding. And what they really wanted was a way to do conformal cooling channels around their molds. Well, how do you do conformal cooling? Oh, well, what we really need is a layer-by-layer process to do really complex geometries. So they changed their entire business. They still do the injection molding, but their other new division is making machines to make tools. What's interesting is they actually print these on a substrate. You have a honeycomb material that actually anchors the part down to prevent the residual stresses from curling the part. So that's sort of an unknown secret, I guess, if you will, of the technology. But these are really complex shapes, straight out of the print, fully dense metal parts. And you'll notice that really has sort of like sand cast surface finish. But on the underside, we're still working on this. The surface finish is a bit rougher due to those anchors that are there. Interesting to note, people always ask about material properties. Right now, what we say is that these processes have the same material properties of cast, but not yet as wrought. That's sort of the transition point. That's what we're hitting right now. Another process, this is selective laser melting. And what we're doing on this print, and this was the CEO in Germany who gave me the video, so I use we as the globe, I guess. What they're making is a 2-inch cube. Okay? On the left, you'll see they're making a solid cube. You'll see it takes a while to do that. This is an earlier generation of the machine. So they're making a fully dense solid cube. On the right, what they made was that cellular cube. Okay? So again, with a cellular, all it is a bunch of dots. I'm going to go back and show you how fast that was. One layer. So the thing is that what we say in additive is we say complexity is free. Meaning, in traditional manufacturing, the more complex a part is, the more expensive it is. But here we say it's free because I can make in the same batch, I can make every part different. It doesn't matter how complex or not complex it is, it takes the same time. But actually, in some cases, complexity is cheaper because it's much faster to make the lightweight, more organic structure than it is to make this big bulk of material that we really don't even need. And so that's one of the new things that's coming through additive is, again, that redesign, that rethinking, making fully dense metallic parts, even some that have these sort of cellular shapes. These are some parts from a friend of mine, Brent Stucker at University of Louisville. Again, you can sort of see the complexity of the shapes relative to the size. This is that little monster from Monsters, Inc. I don't know, tiny little thing. This is a model of this is a normal size keyboard. I mean, this is small stuff. A 9mm with a sliding thing. I can tell how often I use 9mm. But again, and looking at types of hip implants and things like this. Okay. The Department of Energy is very interested and very invested in this technology, especially at Oak Ridge National Labs. And the question is, well, why? It's because it's about energy. Think about this, we're not wasting any material. We're not taking the granite and carving out David. We're only using the material where we need it. So we're using less material and less energy to make much more complex and sophisticated products. This, again, is a fully dense metal gauntlet. These are printed and then reassembled, but you can see, shapes that just can't be made by any other means. One more technology, it's very similar to this, almost the exact same idea, except instead of using a ND YAG laser, it's using an electron beam. So you have an electron gun, basically, that's shooting down into your part. Instead of using mirrors to reflect that beam, you're actually using a focus coil, or a coil to sort of change the direction of electrons. The reason why that's exciting is because it's a much faster process. So this is at preheating the powder bed to get all the powder ready to be melted. And then there you go. One whole layer being scanned and sintered. This is titanium at once.
What's the temperature that you're operating at?
Oh, this is not my machine. I'm trying. It's going to be the melting point of titanium, right? Yeah. There you go. How about that for an answer? Yeah. So this is a much faster process. The surface finish is not as good. The material properties are about the same, and it can only do with conductive metals, but a pretty nice process. So again, really intricate internal geometries, impossible shapes that just can't be made by any other means. One more direct metal technology that's of interest is what's called laser engineered net shaping. Basically, it's a robotic arm, 5-degree freedom robotic arm. In the center nozzle is a high-powered laser. On the right-hand side are powder feeders, basically just shooting powder, metal powder, directly into the hot spot, into the focus of the laser. Now, this technology was originally thought, oh, well, we can start making metal parts this way, but it's really slow. The surface finish is terrible. The layer thickness is very high. Where it's finding its value is in part repair, and especially in the turbine blade industry, because now I can just take old worn blades, just re-tip them and put them back in the market. We see, especially folks like in the Navy who have large cast parts, where this technology is just not going to be able to make something that large, so they do their traditional casting work, but then go in and add features that can't be made by any other means selectively. One more emerging technology that I think that is sort of sneaking up on people is this. It's a completely different industry. It's direct writing. What this is an extrusion nozzle, except what it's extruding is a conductive paste, so nano silver, nano copper particles that are being drawn. You're just drawing a circuit. And the reason why that's really neat is because when you integrate that with additive manufacturing, you can start printing parts with embedded circuits, embedded sensors, embedded power. So friends at University of Texas El Paso have done a lot of great work where they're printing, UAV wings with embedded antennas, embedded circuits. They printed antennas onto soldiers' helmets that conform to the curve. At the Dreams Lab, we're working on things where we're trying the similar process, but with that object flexible material. So now we're having flexible circuits, and we can print strain gauges and actually be able to do closed-loop control of goods through that technology. Okay, so why is this so exciting? Why do the economists call this a manufacturing revolution? Let me ask my high school students in the back. How many of you have purchased a CD? Have you purchased a CD in your entire life? When's the last time you purchased a CD? Years. And how old are you? 18. Well, that's okay. All right. So your parents bought this thing called an 8-track or record. There's this power of the digital thread of additive that's changing the way that we do manufacturing, consumption, and distribution of goods, just like the MP3 did for music. When's the last time you all bought a DVD? Maybe more recently. But what do you do instead? You just download it. How many of you, don't raise your hand, how many of you maybe have consumed some sort of music or movie that maybe your friend purchased that you did not purchase, but you were lent? Does that sound familiar, maybe? Okay, yeah.
They know somebody that
Yeah, they know, there you go. Yeah, you learn from that answer. Okay. So the digital piece is going to change and has changed the way in which we do business. And going back to the prototyping, it's going to increase the number of iterations we can do in the same amount of time. Again, I mentioned complexity is free. And we don't talk about batching anymore. We can do batches, but all the pieces can be unique. So we go back to the Invisalign braces. This is what a build tray looks like to that company. Meaning they process about 200 braces at one time, and every single piece is unique to a unique customer. They do that overnight without looking at it. And that's the next step. And this is where some people sort of get a little concerned. We can talk more. I would love to answer more questions about this. It doesn't take a lot of operator expertise to do this. The Dreams Lab, we hit print on Friday afternoon, and we come back on Monday, and the part's done. We haven't been there. Everything's good. And it's a single tool. I have no tool changes. I don't have to, the same laser, the same extrusion nozzle, the same inkjet heads make big stuff, makes really small stuff. It doesn't matter. We talked about with the wrenches and the brain gears that we can reduce assemblies quite a bit, and we can integrate the parts all together. We'll talk more about this. And of course, as I sort of alluded to, it's about limited waste. So our friends at NASA Langley put this chart together. So traditionally, they want this part made of titanium. They buy a 5,000-pound forged billet, and they throw it all away. Because what they really want is this. So what they call it is a buy-to-fly ratio. They spend $20 For every $20 they spend on material, they only get $1 in return. But with additive, you only use the material you want and only the material you need, and you have full control over where that material goes. So your buy-to-fly ratio is significantly improved. But then there's that question mark, right? So is this really going to change everything? Currently, and it won't be for a while if you ask me, it's not really built for economies of scale. It used to be called rapid prototyping, and that's because it was relative to, I go down to the machine shop, can you make this for me? 3 weeks later, here you go. Oh, that doesn't feel right. Do it again. So it is rapid, but still, we say on average, it's about an hour and a half per vertical inch. And there are some physical limitations about how fast we can move something and melt and then solidify, polymer. Injection molding will always beat us. Well, almost. We'll talk about it. And so there's a study back in 2006 that shows that sort of trade-off curve. Again, injection molding, I've got to invest so much money in tooling that for the low volumes, it doesn't pay off, where this does. Here, there's no tooling, so I just have a constant line no matter what the volume is. And again, I still have to have a job. So there's still a lot of research that has to be done. The material, so Jerry and I have very similar laser sintering machines. Depending on the humidity of our rooms, our products can come out a little different. The metals are a little bit more forgiving, but there's still a big concern about repeatability and certification. So NASA really wants to do this. DoD would love to use this technology because they only make a dozen F-18s a year. NASA builds one rocket engine a year. So why would I invest all that tooling to make one thing? And I have a lot of money put into this. It's a highly engineered system. But NASA's just not quite ready to go lift an engine with a technology they don't quite understand yet. So there's still a lot of work to be done there. So I'll piggyback on what was mentioned earlier about what differentiates AM. When does this make sense? Complex geometries, custom geometries, low volume production, and assembly reduction. Just want to quickly hit on a few of those. This is a great example from out there related to F-18. So this is the traditional manufactured air duct. So it's a non-load bearing part. It provides airflow into the cockpit, and you can see that it takes 16 parts plus glue, so it means it can't be it can't be disassembled. Well, and think about this. Everything that we have that's man-made, it has a shape because manufacturing dictates that shape. We're bound by the constraints of manufacturing, but not anymore. So we just redesign that shape so this is one piece. The reason why we have to assemble this is because I can't do these curves. Well, this technology can. So a lot of savings, no assembly. Think about how costly assembly is, and can be made or can be grown, as they say. We're not going to be quite ready to be printing 4 Tauruses yet, but what has been done on low volume production, right? Custom dashboards are 3D printing on the Bugatti. This is on their Berlin show floor. It was mentioned earlier, the prosthetics. So your CT scan is just a bunch of layers, right? So you can reassemble those layers, and here's your CT scan in physical form. So this is my head and my deviated septum, which you're welcome to pass around. I think everybody in the state of Virginia knows about my deviated septum. That's good. But as a surgeon, they can plan their surgery ahead of time. But again, if I'm a soldier and I have an IED explosion, I need a skull plate. What I can do now is actually take the healthy side of my skull, print that in titanium, and match that perfectly. Instead of having the surgeon cut me open and then take some titanium and just sort of hammer it out a little bit and see if it fits. Knees are being printed, prosthetics that are custom fit are being made, and they're being made to look nice. Hip implants. So in your acetabular cup, we can actually print those titanium pieces now such that the surface is more acceptable to bone. The porosity matches that of bone. That's modeling and simulation, this idea of changing things through design, putting material only where it's needed. This is an example out of Airbus. Their traditional bracket for attaching their seats to the floor. Every single ounce of metal that I can cut off an airline saves me a lot of money in gas. So I just redesign the product so that I have material only where the stresses are, and I don't need material where there's no stress. So I can recreate those products and make them much more lightweight and still meet their performance metrics. Another example out of Virginia Tech, through collaborations with NASA, again, making aircraft wings that have conformal spar and ribs formations. Some other work that's being done where people are printing unmanned aircraft. Again, if you hold that at the light, you can see the entire insides are completely hollowed out and trussed. Again, lightweight, very stiff. That's all printed at one time. And it's not just, toys and trinkets that we bring. These are real things. So F1 Racing is a huge user of this technology. NASCAR is coming on board. These high-value, high-engineered systems with low-volume production are using these technologies. So I probably am running out of time, and so I won't really have a chance to talk a lot about what we do at the Dreams Lab, but let me just show you a quick video, because I think it does a nice job of what we do. What we do is basically do research in the areas of additive manufacturing with the sole goal of helping transition to it to be a manufacturing platform. Welcome to the Dreams Lab, where we do research on additive manufacturing or 3D printing technologies. The Dreams Lab is home to one of the most diverse collection of these technologies at any academic setting in the United States. We have 5 different technologies over 8 different machines that look at different ways of creating products layer by layer from the bottom up. So we have one technology here, the object printer, that actually prints with an inkjet printer droplets of a liquid photopolymer that turns solid when exposed to UV light. In the back here, we have the laser sintering machine, which actually uses a laser to selectively melt powder layer by layer. We also have a machine here that actually prints glue into metal powder, which allows us to make metal parts. And at the VT Fire facility, our foundry on campus, we actually have another printer that prints sand. We can create sand molds for metal casting. What really gets me excited about additive manufacturing is it can fundamentally change the way in which we design products. An example here is a group of seniors in mechanical engineering are redesigning an autonomous quadcopter. And inside this duct is a cellular material, almost like a honeycomb, very lightweight and very stiff material that's very intricate. No other manufacturing technology can make this geometry. No longer are we constrained by traditional manufacturing technologies and their rule sets. All of those rules are now gone. We can create shapes that just can't be made by any other means. So I hate to watch that video, actually, but since you can't come to the lab, if you're not there, it's nice to see it, I think. And we have a lot of great equipment. A lot of what's that DCC has, a lot of great stuff. And like I said, I won't do talk a lot about what we have as far as the research, but in general, we try to advance materials, advance design, and advance education. And that's sort of where I want to end, because we talked a lot about workforce development. We do a lot of work in K-12 STEM, a lot of outreach that was mentioned earlier. We have a new grant starting in this coming summer where we will have teachers spend 6 weeks every summer for 3 summers to do research in the areas of manufacturing. Those teachers will not only get a stipend and continuing education, they go home with a 3D printer. We'll have 36 teachers in the region with 3D printers in their classrooms, and they will have curriculum to teach about 3D printing and manufacturing. We do a lot of undergraduate projects where students are designing products for this technology, because that's the key for workforce development, is not only teaching people about the science of the technology, but teaching them how to design products. Think about this. Not them, we have gone through schooling where the schooling is, you can't do that. So we don't even think of the ideas of what's possible. We don't think in these organic structures. We're trying to change that for their sake, so that when they come to us, they don't think about what's impossible. Let me end one more. We have this one nice thing, and then I will be quiet and I'll take questions. This is our new thing. We call it the Dream Vendor. It's our 3D printing vending machine. It's in the lobby of our Randolph Hall at Virginia Tech. And our big challenge is, how do we get as many hands on this technology as possible? So we sort of came up with the idea of, just make it a vending machine. This is a vending machine that makes things. So you don't go to the vending machine and ask for Snickers. Oh, there's no Snickers. I guess I'll settle for Milky Way. Instead, the inventory is in your hand. There is no inventory on the machine. It makes it right there. So students walk up, put an SD card, and hit go.
We're in the lobby of the Mechanical Engineering Department in Virginia Tech. This is our Dream Vendor. This is the only 3D printing station of its kind that allows students to have free access to it and control over it. I originally started in engineering because I really loved robots. And when I discovered 3D printing, it's like a robot that actually makes something. So that was really exciting to me. These are from MakerBot Industries. They're called Thingomatics. The machine's been open for about 2.5 weeks. We are not able to count how many people have been using it. It's been running nonstop. We're in the CAD lab of the Department of Mechanical Engineering. In our lab, we had this handheld microscope that we needed a stand for. So we took some measurements and created it all in this 3D modeling program. From there, the program will generate the G-code that you will put on an SD card, and then you'll take it to the Dream Vendor. Put the SD card in the slot. We're going to select Build from SD, and then you just pick your file, and then you hit OK, and the printer prints your part. It's like a hot glue gun. And so it shoves this plastic through the nozzle and extrudes this molten plastic. And from there, it draws the pattern of each layer of the part. It's pretty amazing how intricate the parts can be that can come out of this machine. We've had chess pieces, action figures, we've had really complex objects. The finished part will come out into this bin, and so when it's done, you'll just grab your part. So this is the object I created. I designed and printed on the Dream Vendor. It's for my microscope. Sits in there, and it allows me to look at my test samples. One of the things I really like as a researcher in 3D printing is getting to see people's ideas for the use of 3D printing. You know, I can only think of so many things that this technology can do, and opening this up to the public really helps our research out because we get those ideas from other people.
So the point is, we've got a bunch of young folks who have dreams. And they have, that was not meant on purpose. We got a lot of young folks who have a lot of good ideas. And they've never been able to take them to production because manufacturing is what costs. They have to invest $15,000 to get a tool made. That is changing. Again, it's not, the manufacturing is not the barrier to entry anymore. It's the design, it's the idea, and it's about democratizing manufacturing. And that's really the great power of this technology. So with that, I'll close and answer questions and invite. So thanks.